This is Bob Capetta, and this lesson is DeMorgan's Laws in Logic. So we're going to use truth tables to prove the first of DeMorgan's laws, namely the negation of P and Q is equivalent to the negation of P or the negation of Q. So we start with our standard PQ list, P, T, T, F, F, Q, T, F, T, F. So I'm going to need to do P and Q. Remember, P and Q means both have to be true simultaneously. T and T, yes. TF, no. FT, no. FF, no. So true, false, false, false for P and Q. Next, we're going to take the negation of that. So every true becomes false, every false becomes true. So the negation of P and Q will be false, true, 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 which we have. So we've done the truth tables for the first statement. We want to show that that is equivalent to not P or not Q. So we need to construct not P. So P is T, T, F, F. T becomes F. F becomes T for not P. So not P will be F, F, T, T. T becomes F. T becomes F. F becomes T. F becomes T. That's not P. Not Q. T becomes F. F becomes T. T becomes F. F becomes T. So FT, FT. For not Q. And then we finish off with an OR. Remember, OR on these two. It's got to be true in one or the other or both. One or the other or both. Last one's both. Second to last one, yeah, this one's true. Second one, this one's true. But the first one, none of them are true. So the first one fails the OR test. We don't have a true in one or the other or both. So the first one is false, but the other three are all true. So we've done truth tables for not P and Q. We've done truth tables for not P or not Q. Let's take a look at what we have. FTTT, FTTT. They are the same. When that happens, we can conclude indeed that those two statements are equivalent. So let's look at this for a minute. Not P and Q, not P or not Q. So you take the negation of the first one, change from an and to an or, take the negation of the second one. So again, negation of the first, change and or, negation of second. That's how the first version of DeMorgan's law works. So let's use it. The first example we're going to say is that Joe has a bachelor's degree and a nice car. We want to negate that statement. So we want to say that is not true. So what will that be? The first statement, P, Joe has a bachelor's degree. Second statement, Joe has a nice car. So our original statement is P and Q. Joe has a bachelor's degree and a nice car. P and Q. So if I want to negate that, not P and Q, negate the first. Change and or, negate the second. So that's our process. Negate the first, change and or, negate the second. Negate the first. Joe has a bachelor's degree? No. So Joe does not have a bachelor's degree. Or Joe has a nice car? No, Joe does not have a nice car. So Joe does not have a bachelor's degree or Joe does not have a nice car. That would be the negation of that original statement. Let's take a look at one more example in that same sort of vein. Mary has a computer, but she doesn't have a television. Remember, but, yet. Furthermore, these are examples of and. So I have two statements here. First one is Mary has a computer. That's a P. Q, I'm going to say Mary has a television even though she does not have a television. So my statement, Mary has a computer and she doesn't have a television, but is essentially the same thing as and, will be what? Will be P and not Q. So we want to negate that using DeMorgan's law. So negate the first, change the and to an or, negate the second. That will be our process. Again, negate the first, change and to or, negate the second. So what am I going to have? Negate the first, not P or not Q. And what is not Q? Not Q is, of course, Q. So let's go back to the context of the problem, not P. P was Mary has a computer, so not P is Mary does not have a computer, or Q, or Mary has a television. So that will be our final statement that negates the original statement that we had. Okay, so that's one version of DeMorgan's law. Negate the first, change and to or, negate the second. Now we're going to look at the second version of DeMorgan's law. The negation of P or Q is the negation of P and the negation of Q. So notice this one, negate the first piece, change from or to and, negate the second piece. So there's a certain similarity in both versions of DeMorgan's law. So we want truth table, so I will first need P or Q. Remember, P or Q is if one or the other or both are true. So true, true, certainly that's true, true, false. First one is true, false, true. Second one is true, false, false. At least one of them true. Nope, that's false. So that's P or Q. Then we need not P or Q. So T becomes F, T becomes F, T becomes F, F becomes T. Taking the negation of P or Q gives me F, 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 T. I'm going to then need not P and not Q. Now how about not P? P is T, T, F, F. If I change it to not, it'll be F, F, T, T. How about not Q? Not Q is T, F, T, F. So change T to F, F, T, F, T. So there you go, not P, F, F, T, T, changed. Not Q, T, F, T, F becomes F, T, F, T. And then I want the and of these two columns, not P and not Q. Not P and not Q is true if both are true. Where are both true? In the last slot. The last slot is T, T. So the last slot both are true, but the other three, they are not both true, so those are all false. And our goal was to prove DeMorgan's law. Have we shown that not P or Q is the same as not P and not Q? Not P or Q, F, 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 T. Not P and not Q, F, 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 T. So those two are the same. So if that's the case, what do we conclude? We conclude not P or Q is equivalent to not P and not Q. So again, what is our strategy here? Not P or Q, not the first, change or to and, not the second. Not the first, flip the sign, not the second. That works for both versions of DeMorgan's law. So let's see if we can understand this by looking at an example. It is not true that a team from California or an American League team won the World Series. Pick a year where that was the case. It is not true that a team from California or an American League team won the World Series. Let's say that's what we're looking at. So we've got to define the statements. We want to use DeMorgan's law to express this in an equivalent manner. P is a team from California won the World Series. Q is an American League team won the World Series. So it's not true that either a team from California or an American League team won the World Series. So it's not true California or American League. It's not true that P or Q won the World Series. Therefore, it's not P and not Q. Not P. A team from California won the World Series? No. So we'll have to say a team from California did not win the World Series. Flip that sign. And an American League team did not win the World Series. So that is our negated statement of the original one by using DeMorgan's law. Not P or Q, not the first piece and not the second piece. All right, let's look at something that I've looked at in previous videos, namely that P implies Q, which is the same as if P then Q, is the same as not P or Q. Remember, P implies Q. If the first thing happens, the second thing has to happen. Here, the first thing happened, but the second thing didn't happen. Remember, we have a TF strategy. If you have a TF, then you know your P implies Q is false, because the first thing happened, but the second thing didn't. That's false. But all of the other cases are true. So the TF is your only false for a P implies Q, assuming P is on the left and Q is on the right. Now, we also want to construct a truth table for not P or Q. So we need a not P column. P is TTFF, not P, FFTT. Boom. Let me go ahead and copy down the Q column, TFTF next to it just so we can see it. Q, TFTF. We want to go or. So when is or true? When one or the other or both are true. False, true. Are they one or the other or both true? Yes. False, false. One or the other or both true? No. True, true. One or the other or both true? Yes. True, false. One or the other or both true? Yes. So the only false is the second one. The others are all true. And we get true, false, true, true. So here we have if P then Q, TFTT, not P or Q, TFTT. So we'll circle those and demonstrate that indeed those are equal. So that's going to be helpful for us to negate that statement. If P then Q is the same as not P or Q, we want to negate that. So how do we negate P implies Q? How do we negate if P then Q? Well, what do we know? P implies Q is equivalent to not P or Q. That's what we just said. We just proved that with the truth tables. Now let's negate both sides. The negation of P implies Q is the same thing as the negation of not P or Q. So let's look at this piece here, the negation of not P or Q. Here is where we're going to use DeMorgan's law. And how does that work? Not the first piece, flip the sign, not the second piece. Not P and not Q. Not P and not Q. Again, not the first piece, flip the sign, or becomes and, not the second piece. So not P, of course, is just P and not Q. And we get our rule for the negation of if P then Q. And notice the first one is true and the second one is false. So that's our TF example that we showed. TF gives us a false. That's where that's negation is true. So that satisfies that requirement. So let's go ahead and use the fact that the negation of P implies Q is the same as P and not Q. And let's see if we can rewrite this in an equivalent manner. So it is not true that if you study for a mathematics exam, then you will pass. It is not true that if you study for a mathematics exam, then you will pass. It's a good idea to study for a mathematics exam, but it may not be enough. You may need to have prerequisites and other sorts of things. So we want to explain this in a similar manner, an equivalent manner, using symbolic logic. So what are our events here? What are our statements? P is a statement that you study for a mathematics exam. Q is a statement you pass the mathematics exam. Okay. So if you study, you will pass as P implies Q, but we want to go with the negation of that. Again, if you study for a mathematics exam, then you will pass. If that is our statement, that is P implies Q. That is if P, then Q. How do I negate that? If I negate P implies Q, what we just did on the previous slide was P and not Q. P, what is P? You study for the mathematics exam, and not Q, and you don't pass the mathematics exam. That is the counterexample, right? That is the counterexample that says if you study for the exam, then you will pass. Certainly that is not true in every single case. Let's take a look at one more sort of example. I want to take a look at P implies Q or R. So if P is true, then Q or R must be true. We want to take the negation of this statement. Now let's remind ourselves of what we said previously. The negation of P implies Q is P and not Q. But since we have P's and Q's in this rule together with this problem, it may be difficult to use that. So I'd like to rethink this. The negation of first implies second. If I think of P as the first and Q as the second, the negation of first implies second is first and not the second. Right? So the negation of if then is the first and not the second. And our question here is the negation of P implies Q or R. So the first is P, and, so we know what our and symbol looks like, not the second, not Q or R. First and not the second. First is P, and not Q or R. Now, do we know how to do not Q or R? That's where DeMorgan's law comes in place, right? Not the first, flip the sign, not the second. So not Q or becomes and, not R. Not Q and not R. So I get P must be true and not Q must be true and not R must be true. And the nice thing about ands is I don't need to worry about order of operations here. P is true and Q is not true and R is not true. So our final answer is P and not Q and not R. That is our negation of if P is true, then Q or R is true. So what did we show in our DeMorgan's laws? What did we look at? We had this one, not P and Q is equivalent to not P or not Q. Again, not the first, flip the sign, and becomes or, not Q. That was our first example. What was our second example? Was where? Can I find it? There we go. Not P or Q, not P or Q is equivalent to not P and not Q. Again, not the first piece, flip the sign, or becomes and, not the second piece. So not P or Q is not P and not Q. And then we just finished with this last little piece that we had, right? Where we showed P, if P then Q, that's equivalent to not P or Q. And then what did we use that to prove? We use that to negate if P then Q. And what did we get? We got the negation of if P then Q is the same as P and not Q. So that is also helpful for you to use. And that will conclude this lesson.